Hey guys, welcome back. Before we get into the t-based sampling distributions and confidence intervals, I realized I didn't cover all of the z-based. So we're going to finish up on that, and we're going to do that before we get into t-based. So I'm just going to start right in on the problem solving. So we're going to be looking at number 2 and number 3 on our worksheets, and going from there. Based on the standard normal probability distribution, we know that 95% of the values of a normally distributed random variable are within how many standard deviations of the mean. So we actually just did this in our last video. We found this number to be 1.96. That's our z value. That means that 95% of the values are within 1.96 standard deviations about the mean, so plus or minus 1.96. Okay? And I'm just going to go ahead and answer these for you, and I'll let you go into the z-table and look up. Actually, I guess I'll do one for you. I'll do one for you, and then I'll just I'll answer the rest, and I'll let you go about trying to figure out how to do that after I just show you the one. So I'll go ahead and write these in. So we have plus or minus 2.58, plus or minus 2.33, and plus or minus 1.645, or I usually just go with 1.65. But the reason why I give you the 1.645 is because I think in the Connect homework a lot of the time they like this number better. But I'm fine with either number, like on a test or in your case or whatnot. So that's that. So let's go over to the z-table and let's look at how we go about finding these numbers. Okay, so we are at the z-table. Which one do we want to find? I guess let's find 99%. Okay, so the way that we think about this, so we want to find the z-value for 99%. The way that we think about this is we go and we make our normal curve. That's not very good, is it? Okay, so that's a normal curve supposedly. We make our normal curve, and we decide, okay, we're looking at a 99% confidence interval. So we have edges here, and we need 99% of the probability on the inside. Okay, so that means we need 1% on the outside. We need 0.01 on the outside, which means each tail is going to have half of that 1%. So it's going to have 0.005 and then 0.005, right? So we have two different ways to go about this. If we want to look at the positive z-value, we can look at the point where 0.995 is below it, so going back that way. Or if we want to look at the negative z-value, we can look for where 0.005 is below it. I say let's just look at the negative one, okay, because that's going to help us, or that's just going to be easier. So go over to the table. Now let's go to the negative side of the table. And now let's look for 0.005 on our table and then find the corresponding z-value. So I'm just going to go down like this until we start to get close. 0.001, 0.0019, 0.002, 0.0035, 0.0047. Okay, now we're getting close. Moving to the right, our numbers are getting smaller, so that doesn't help us. So now we go down to 0.0062. So now let's move to the right. 0.0060 all the way over here. 0.0051, 0.0049. I like this one better because this is leaving a smaller amount of area to the left of the curve. So this is a negative 2.58. Negative 2.58. Boom, right there. 2.58. That's where we get that 99% confidence interval. Similarly, if we wanted to look at the positive version, we would look for 0.995, right? So that's because that only leaves 0.005 probability or area to the right of the curve. So we're looking at 0.995 to the left of the curve. So if we look at the positive table, or the right side of the curve, I should say, we're looking for 0.995. So going down here, we get 0.9918, 0.9938, 0.9953. Okay, we move to the right. That's getting larger, so we don't want that. So now we're at 0.9938, all the way over till we get to 0.995, 0.9951. We're at 2.5, 8. Perfect. That's where we want to be. Plus or minus 2.58. So go ahead on your own. Try the 98% one and the 90% one. It's just good practice to just play with the tables and figure out how you want to do that, okay? So we'll move on. In an effort to estimate the mean amount spent per customer for dinner at a major Norca restaurant, data were collected for a sample of 49 customers over a 3-week period. Assuming a population standard deviation of $2.50, what is the margin of error at a 95% confidence level? So margin of error is just talking about, in terms of our confidence interval, if we define our confidence interval as the formula of x bar plus or minus z of alpha half, so the z that corresponds to leaving half of alpha off to the side, times sigma over square root of n, right? So our sigma x bar. If we define it like that, then the margin of error, so the MOE, I guess we'll call it, margin of error, is just referring to this, we'll say refers to just the plus or minus z of alpha over 2 sigma over square root of n part. That's our margin of error. So we're deviating from sigma x bar in that regard, okay? So in order to calculate that margin of error, so we have a 95% confidence interval. We know that the z that corresponds to that is 1.96 because we just found that, 1.96 z. So that's our z of alpha half. So this would be equivalent to plus or minus z of 0.025 because alpha is 0.05. So alpha half, 0.025. It's 1.96 times the population standard deviation of 2.5 divided by the square root of n. Okay? And that's just going to end up being plus or minus 0.7 or 70 cents. Essentially. Oh. So that's our margin of error. Okay, and now if the sample mean is 22.6, what is the 95% confidence interval for the population mean? Okay, so that's easy. So we already got the margin of error. If the sample mean is $22.60, we're just saying, okay, well, it's $22.60 plus the 70 cents here and minus it. So we get 21.3. Nope, sorry. Ooh, I wrote that wrong. 22.6. We get 23.3 and 21.9. Okay, and so then our 95% confidence interval is going to be from 21.90, so $21.90, to $23.30. So that is the 95% confidence interval for the population mean. So what does that mean in layman's terms? That means that given the sample of 49 customers that we took over the 3-week period, assuming that we knew the population standard deviation of $2.50, so that's the standard deviation of prices of dinner spent, we can assume with 95% confidence that the true population mean, like the true cost of a check, right? So if we could somehow sample every single, not sample, if we could somehow have every single data point, we would know that the mu, like the true average cost of a meal at this restaurant, we can say within 95% confidence is in between $21.90 and $23.30, right? So this is the power of running these confidence intervals. What we do is we take a sample. So we're a person standing outside of this restaurant. We take a sample. We take 49 samples, in fact, and we make some assumptions. Like we assume that we have a population standard deviation, which we'll see going forward. We're going to kind of alleviate that assumption. But we assume we have a population standard deviation. And because we have that, we can come up with a confidence interval to where we actually know with 95% confidence that the true mean, like the true average price of a meal, is in that range. So that's what that is. This is what it's all about. Then it just says, how does your answer to part B change if you use a 95% confidence interval instead of 99% confidence interval instead of the 96, right? So we're just going to be using a different different z-value. So the 99% confidence interval implies a z-value of 2.58. So that's going to imply that we use that 2.58 in this formula, right? So we're going to have 2.58 times 2.5 divided by the square root of 49. And that is going to equal, this whole thing is going to equal 0.9214. And if we plug that 0.9214 into here, like this formula, we're going to end up getting an interval. So adding it and subtracting it from the 22.60, we're going to end up getting an interval of 21.67 to 23.53. So now this is a range that we have 99% confidence in that the population mean is within it. How does your answer to part B change if we sampled more people? If we sampled 100 people rather than 49? Okay, so we run this again. So I think we're going to be running this now with our 95% confidence interval. Yeah. So we're not going to run it with the 99. We're just going to run it with the 95. But basically, we're just going to go ahead. I'll just calculate it all at the same time here. Plus or minus the 1.96 times the standard deviation of the population divided by the square root of n, which is no longer the square root of 49. It's going to be the square root of 100. Notice how we use nice round numbers because those square roots tend to be easy to calculate. Square root of 49 is just 7. Square root of 100 is just 10. And this is going to give us a range here. And I'll just go ahead and give it to you here, and you guys can actually run the calculations. So that's that. So what happens when we increase the sample size? When we increase the sample size, our confidence, our 95% confidence interval becomes larger, right? So we're looking at B, so look at B and then look at D. So we have a 95% confidence interval . excuse me, I misspoke. Our confidence interval actually becomes smaller, and that's a good thing, right? Because the smaller our confidence interval is now we have a smaller area that we have 95% confidence in, meaning we are honing in on actually where that population mean is, right? So we still have 95% confidence. So we've got this massive amount of confidence, but it's in a smaller area, which means we're getting more accurate. We're getting more precise with our we're not getting more accurate. I guess we're getting more precise with where we're looking for our 95% confidence. Okay. All right, so number 4 is going to deal with the t-distribution. So we're going to get back to the PowerPoint slides and we're going to look at that. Okay. 8.2 t-based confidence intervals for a mean of sigma unknown. Okay, so that heading kind of tells you all you need to know with t-based, other than actually learning how to use it. Okay, so I'm just going to explain t in layman's terms. What we actually do with t is a distribution that looks a lot like the normal distribution. It's very much shaped like the normal distribution. As n gets large, meaning as we use a larger and larger sample, t is going to look more and more like a normal distribution. It's going to actually mold into the normal distribution. But the way that t differs from normal is that we can't use sigma. So sigma is our population standard deviation. But think about this. How ridiculous is it to make the assumption that, like, we're trying to learn all this stuff about a population or population distribution, but yet somehow we're trying to learn all this stuff about the population distribution, and somehow we just happen to know the standard deviation of it. It's like, well, if we knew the standard deviation of it, like, doesn't that mean that we probably know other stuff about that population? So that's kind of, that's kind of the thing that maybe you didn't realize when we were doing the last problem. Okay, and this is kind of the concept that I was talking about in the first video of we kind of learn it backwards. We kind of learn it from the perspective of, like, we want to learn all these distributions, and then we want to start to kind of peel away some of the assumptions that we have in order to kind of apply it to the real world. Okay, so the t-based is more accurate in terms of real world. And the reason that it is because we don't make any assumptions about the population standard deviation. So for t-based, we either need to be given a sample standard deviation, or we need to be given the sample data, and then we actually then calculate the sample standard deviation. Okay, so z is when sigma is known, so we have a population standard deviation known, and t is when sigma is unknown, so then we end up using a sample standard deviation. That is the difference. That is the difference between the two. So that might be something that you look for on a test. I'm sure there's going to be issues where you wonder which distribution to use. If we know sigma, it's going to be z. If we don't know sigma, it's going to be t. Simple as that. Okay? You see the formulas. T is equal to x bar minus mu over s divided by the square root of n. That is the exact same formula as the z formula, except that we replace sigma with s here. Okay? And it becomes the t distribution. It's symmetrical and bell-shaped. The t-distribution is more spread out than the standard deviation, or than the standard normal distribution. The spread of t is given by the number of degrees of freedom. Okay, a degree of freedom is defined as the size of the sample minus 1. Okay, so if we have a sample size of 40, the degrees of freedom is equal to 39. Okay, and that's how we're going to be looking up values for this in a table. Okay, and I'll show you how to use that in a little bit. Oh, excuse me. The t-distribution in degrees of freedom. As the sample size n increases, the degrees of freedom also increases. That makes complete sense, right? If we have a sample size of 100, we have degrees of freedom of 99. If the sample size goes up to 200, we have degrees of freedom of 199, right? So it's going to increase by 1 unit just as the sample size is. As the degrees of freedom increase, the spread of the t-curve decreases, right? So it's going to start to look more and more normal. As the degrees of freedom increases indefinitely, the t-curve approaches the standard normal curve, which I just mentioned. If n is greater than 30, so degrees of freedom is n minus 1 is greater than 29, the t-curve is very similar to the standard normal curve. So this n equal 30 number is going to be something that's very important. We're gonna like pose questions like, is n large? And the number, or the description large is, sounds subjective. But this is what we mean. We mean greater than 30, greater than or equal to 30. Okay, that's what we mean by large for n. T of alpha is the point on the horizontal axis under the t-curve that gives a right-hand tail. So this is going to be a cardinal difference between the way that we look at these tables. Note this picture right here. This picture shows the curve of the t-distribution having degrees of freedom, and that area under the curve, alpha, is the area to the right of the curve. So it's not the cumulative area. The cumulative area is how the normal distribution is done. The t-curve is giving you the alpha area, okay? So the inside part of the t-table are going to be t-values, right? So that's not the same as the normal distribution, where the inside of that table were probabilities, okay? And then the outside was the z-values. Okay, so the value of the t-alpha in a particular situation depends on the right-hand tail area alpha and the number of degrees of freedom. This is what this table looks like. So if I wanted you to look up a 95% confidence interval for a sample size of 15, so I'll just write this here. We'll say 95% confidence interval and n equal 15. What's the t-value that you would use? All right, well, we're looking up degrees of freedom. So we have n equal 15, so we know then degrees of freedom is equal to 14. Okay, so we go all the way down here at 14. Lo and behold, it's highlighted. It's almost like I did that on purpose. 95% confidence interval. So for a 95% confidence interval, if we're looking at a curve like this, we want 5% of the alpha, right, on the outside of that confidence interval. So here's the confidence interval. We want it inside here. So 5% is going to leave 0.025 on one side and 0.025 on the other. This table is set up such that this is giving us the right-hand tail data. So we're using 0.025, t of 0.025. So we find where these intersect and we get 2.145. Right, so these t-values are going to change as the degrees of freedom change. So it's not like the z-table where, like, if we're looking for a confidence interval, it's always 1.96. That's our z-value. This is going to be any one of these values, and it's all going to depend on the number of units in the sample, right? Because that's what's going to determine the degrees of freedom, and then that's going to be how far we go down on the table. Okay, and this is just a shortened version of the table. The table that you have in your appendix is going to show a larger version. T-based confidence intervals for the mean. There you go. Another graphical depiction of it. And this confidence interval is going to behave just exactly as the z did, except for the obvious change where we're not using sigma, we're using s. So we're going to have x bar, which is the sample mean, plus or minus the t-value of alpha half times s divided by square root of n. Okay, let's go ahead and work on a problem with this. So refer to number 4 in your worksheet, please. Okay, the following sample data represents a random sample of quiz scores for a normal population. X values are 10, 8, 12, 15, 13, 11, 6, and 5. Excuse me. What is the point estimate of the population mean? So the point estimate of the population mean is just referring to x bar. What is x bar? Well, I don't need to show you how to calculate X bar. You guys know how to calculate X bar. That's just going to be whatever the sample mean here. So we just add all these up and divide by the number of pieces of data. It turns out it's going to be 80 divided by the number of pieces of data, 8. And that's 10. So the point estimate is 10. X bar is equal to 10. What is the point estimate for the standard deviation? That's also a calculation that you can run in Excel. I'm not going to do that. We've calculated sample standard deviation before. We end up getting the square root of 12 and 3.4641. Okay, and let's see if I can't give us a little bit more room to do this problem. Now it's asking, what is the 95% confidence interval for the population mean? Okay, so first thing we need to note is how many pieces of data do we have? We have 8 pieces of data. So if we have 8 pieces of data, let's just note that we have n equal 8. And so then that means that our degrees of freedom, which is just n minus 1, is 7. Okay? So we get a degree of freedom of 7. And it's asking for a 95% confidence interval. Okay? So 95% confidence interval, say 95% CI implies alpha equal to 0.05. Right? And then thus alpha half is equal to 0.025. Right? Because that's what's going to be in our table that we're going to be looking for. So I would go back to our PowerPoint here, and we get X bar plus or minus T of alpha half times S over square root of n. Okay? So X bar plus or minus T of alpha half times S over the square root of n. Okay, so X bar we know is 10. That's going to be plus or minus this T of alpha half, so let's go find that. So T of alpha half, so it's going to be T of 0.025 with degrees of freedom of 7. So let's find the T table. Here is our T table. So first let's find the degrees of freedom of 7 and the T value of 0.025. So 0.025 is right here. Degrees of freedom 7. So the number that we get is 2.365. So I'm just going to note this over here. We're going to say T of 0.025 comma 7. So comma the degrees of freedom is, I already forgot it, it's terrible, 2.365. So then we have 10 plus or minus 2.365 times S, which S is this. So we'll just call it the square root of 12 all over the square root of n, which is the square root of 8. There's a couple of square roots. And when we calculate this all out, we're getting an interval, right? Because we did the plus or minus calculation. And we are going to come up with, sorry, I had to calculate that. The interval of 7.103 to 12.897. That's that. Okay, so that was T. So now we're going to be looking at a different type of problem. So this this formula is going to be based upon the same formulas that we've been using, these Z confidence interval formulas and T confidence interval formulas. So this is just going to be our formula for sample size determination. And so yeah, this is just the formula that you need to know for that. We're just going to say n is equal to z of alpha half, so the z confidence interval level, or the z value for a certain confidence interval, times sigma, divided by e, which e represents the number of units away from mu. Okay? And that whole thing is squared. And that's going to give us the number of the sample size in order to give us a certain level of confidence. Okay, and that certain level of confidence is going to be whatever alpha specifies. So this is our formula for a z-based sample size determination, and this is going to be our formula for a t-based sample size determination. So look at the similarities. N is equal to z alpha half times sigma over e, whole thing squared. And this is n is equal to t alpha half times s, not sigma, over e, whole thing squared. Right, so the only thing that changes is that the z turns into a t and the sigma turns into an s. Same e, same squared, coming up with the same type of calculation. Okay. So let's look at number 5 on our worksheet. And we are going to calculate a sample size determination. Whoa. Waiting for my paper to, or my document to save. Okay, whatever. I'm sure it'll be fine. Okay, number 5. We're going to do a sample size determination problem. We're actually just going to do one that's z-based. The reason why we don't do a second one, maybe we'll just do a second one in the review or something like that. But the reason that we don't do a second one is that these function the exact same way for both z and t. So once you know how to use the t-table, then this type of formula is, it's just going to be the exact same thing. Okay. So, okay, we have the EPA city highway MPG range for a Saturn Vue. Oh geez, they don't even make Saturns anymore. Saturn Vue 4-wheel drive automatic 5-speed transmission is 20 to 28 miles per gallon. If you owned this vehicle, how large a sample size, how many tanks of gas would be required to estimate your mean MPG within an error of plus or minus 1 MPG and 90% confidence? The standard deviation is assumed to be 2 miles per gallon. Right? So because we assume a standard deviation, that means that we're talking about a sigma. Okay? That doesn't mean that, I think if we said it was calculated to be, then we would be talking about an S. But we assume, so we're talking about 2. We're talking about the population standard deviation. So we have a sigma equal to 2. The error is equal to 1, right? So we want to know plus or minus 1. So error is equal to 1. What's our alpha level? Our alpha level is going to be 0.10 because we're looking at 95% confidence. So alpha is just equal to 1 minus the confidence, right? So that's just going to be 0.1. And what else do we need? I guess we need to know the z number that, well, I guess let's write down the formula first. N is equal to z alpha half times sigma all over E whole thing squared. Okay, so what pieces do we have? N is what we're solving for, so that's our question mark. That's what we're solving for. So we need a z value, a sigma value, an e value. We have an e value, we have a sigma value, and then what is our z value? Okay, so now we're looking for our z of alpha half. So we're looking for the z of 0.05, right? Alpha is 0.10, z of 0.05. So this is the 90% confidence interval. We're looking for the z of 0.05. We actually solved for this earlier on in the worksheet. I don't know if you guys recall that, but we did the 95% confidence interval, the 99, the 98, and then the 90. Our number for the 90 was 1.645 or 1.65. I like to use 1.65. So all we're going to do now is we're going to plug and chug here. Plug everything into the formula. N is equal to 1.65 times sigma, so times 2, all over E, 1, and that whole thing is squared. So when we square that, so this is going to be 3.3 squared, which gives us 10.89. Now the first thing I want you to notice, or the next thing I want you to notice, is this n that we're solving for a whole number. We're solving for a sample size. You couldn't have 10.89 pieces of data, right? You couldn't have 10.89 observations. So whatever this number is, you always round up. So I just put an arrow and say 11. N equals 11, right? This could be 10.001, and you still are going to round up to 11, okay? Though I guess in that case you could make a case for 10 because you're not really like losing much accuracy. But say it was 10.4, you're definitely rounding up to 11 in that scenario. Okay. All right, we're going to go ahead and conclude this video with the ending of sample size, and the next video we'll move on to the population proportion and learn how to use that.